Okay, this is the 6th video in the kinematics section, and this is all to do with kinematics in the vector plane. So yeah, up till now, what we've been doing, what we've been looking at are problems, linear problems, just in one dimension. Car moves along a road or whatever. But now we're looking at stuff moving in a plane. Which if we kind of draw this out, and very often these diagrams are useful, we'll either be denoting our dimensions as I and j, sometimes x and y, and very often these problems talk about east and north, so it tends to be rightwards and upwards that we're using as our positive directions. So just an example, really, just to explain what we're talking about here. A particle moves with constant acceleration. At time t equals 0, p is moving in the direction 4i plus 3j. So that is a vector. Now we may have done vectors in pure maths, but quite simply it means that it's for any unit of time, it'll move 4 along in the rightwards direction and 3 up. So it's moving in this sort of diagonal up here. And with speed 15 meters per second, 6 seconds later, p is moving with a velocity minus 12i plus 6j. It's coming backwards in the horizontal sense, but still going upwards at the same time. Right, I'm not going to solve that right now. This is just really to kind of illustrate these sort of problems, to give us a bit of context. So these are two-dimensional problems, and basically we are solving for 2 dimensions at the same time. Fortunately, we can isolate the i's and the j's, the components, and treat them as in 2 parts. So that just adds a bit of complexity to it, but conceptually not too much more difficult. Sometimes, though, we've talked about simultaneous equations before, and I think I mentioned at the time that problems in the vector plane can actually give rise to simultaneous equations, because there may be parameters describing our motion which we have to find out, and sometimes there may be 2 unknowns in each direction, but because we've got relationships in the horizontal and in the vertical direction, then we've got 2 equations in 2 unknowns, so we can solve simultaneously. Okay, so that is that. A vector problem that asks for velocity will require the answer as an ij pair, and very often it does that. I suggest actually, how sometimes the problems will ask for speed and or direction. So we need to kind of understand the distinction between the 2. Usually we have to do all our working out and get some answer, velocity, typically as a vector, and then convert that vector into a scalar, which is what its speed is. And in this example, for instance, if we did have a velocity 4 horizontally and 3 vertically, then just thinking about this triangle of velocities in this case, then the hypotenuse would be 5, so that would be the speed. So our velocity would be this 4i 3j pair, but the speed would be 5, and the direction would be the angle that this hypotenuse makes with the horizontal, which would be the inverse tan of 3 divided by 4. So sometimes that comes into these problems. Something to watch out for in these problems, there are sort of implicit well, some of the questions just require to interpret the vectors, and this is a typical one. When is the particle moving due north? And if that's a question, then basically, if you look at your vector, your velocity vector, then it will be moving due north when it's got no easterly or I component, when that is 0. And if it's a function of t, then you have to just solve that equation for when the I component is equal to 0. So that sort of thing comes into these questions. So kind of watch out for that. The other thing to note is that these problems can also be non-constant acceleration. These are at the harder end of the kinematics. First of all, non-constant acceleration, and secondly, the kinematics in the vector plane. Quite possible that the two of them, get put together, and you get non-constant acceleration in the vector plane. You've kind of got double complexity there. Again, not so as you should be particularly phased about it. The actual rules are a bit more complicated, but it's not. They can be done methodical enough about it. Having said that, if you did get one of those in exam, I think it would be one of the harder problems. Okay, so let's move on and have a look at an example. Well, exactly the example I had above. Particle P moves with constant acceleration at time t equals 0. P is moving in the direction. That's the direction. It's moving with speed 15. Now, this is a slightly obscure way of telling you what the velocity vector is. So we'll come back to that. 6 seconds later, P is moving with velocity that minus 12I plus 6J. So that would have been nice if they'd actually given us the initial velocity in vector form, but they've kind of made it a bit more complicated, just so we have to think about it. And then it says find the acceleration of P. Okay, so the speed 15 is a scalar. We need to split it into two parts in order to find out what the vector is. Not too difficult, but let's see. Now, at this point, one thing I might suggest is that invariably the questions are given in this form, IJ form. And I think just as a tip, it's almost always easier to write these in this form as a column vector with your I and your J. And the reason is, you've got rather complicated statements with I's and J's in, and you have to scan through it to see which are the I parts and which are the J parts. When you write it in a column vector like this, then as we can see from this example here, the calculations are rather more obvious. And in actual fact, it's kind of what you're doing is you're laying out an equation for the I direction and an equation for the J direction. One above the other, and it does. I've always found that it is a lot easier to work that way. Okay, so I flipped over to this. Having said that, if your question is given in IJ form, you need to convert it back at the end and express it back in IJ form and not as a column vector. But all the working in the middle, then that's fair enough for you to actually use whichever convention you wish to use. Okay, so this speed of 15 is a scalar. We need to split it I and J. Well, this is in the direction 4I 3J. So if it's in the direction 4I 3J, it is also in the direction 12I 9J. And if we write it out like that, we can see that this is a kind of triple length 3, 4, 5 triangle. So from that we can easily deduce that the velocity vector is 12, 9. Okay, so that certainly moves in the direction 4i3j, and it certainly has magnitude 15. So so that's fairly straightforward use of a 3, 4, 5 triangle. So that is the velocity. I've denoted it by v brackets 0. Okay, so that's a bit of notation that we introduced back in with the Sudat equations. Okay, so the acceleration is the change in velocity divided by time. Change in time. And we can say that because acceleration is a constant. If it were not constant, we wouldn't be able to do that. But it is constant acceleration. So acceleration is equal to the velocity at time t equals 6 minus the velocity at time t equals 0, v6 minus v0, then divided by delta t, the change in time. So this is the velocity at t equals 6. So it's just a column vector expression of that. This is the velocity at time t equals 0, which is what we've got here. And then divided by the change in time, which is 6 seconds. So if we just work that through, that's minus 24 divided by 6, which is minus 4. And then minus 3 divided by 6, which is minus 0.5. So that is the vector, the acceleration vector. Now, just as that is what it's, in these questions, if they ask you for acceleration, it's a vector they're asking for sort of implicitly. But I've just added this little bit on here because if we wanted the magnitude of the acceleration, then this is where we would use Pythagoras. So it would be the square root of the square of the two components, which comes to 4.03 meters per second. So that's in the direction of the travel, and we could work out the angle as well if we wanted. So so that's just a bit of a bonus section on the question. But the answer to what is the acceleration of p is just there. Okay, so let's go down now. This second example is a bit more involved. I've used a little bit of color coding here because I think it helps. Points A and B have position vectors 3i, 2j, and 6i minus 4j meters respectively, and j in horizontal plane. And the idea of a position vector, incidentally, is a little bit of an odd one. A position is a position, it's not a vector. But it's what it means is it's in relation to a frame of reference where you're sort of starting from the origin 0, 0. So it sort of turns it into a vector. I think it's rather dubious terminology myself, but anyway, we can just not too much as far as the calculation is concerned. If we just imagine a coordinate system, then this is where the points A and B are on that coordinate system. So a particle moves from A to B with constant velocity I minus 2j meters per second. Calculate the time that the particle takes to move from A to B. Okay, so so basically, if we're looking at the displacement, it's basically moving from A to B. So if we actually form the vector of B minus A, then it's the displacement. The displacement is a vector. Then it's just the difference between these. So 6 minus 3, minus 4 minus 2 is minus 6. So that's what it's done. It has gone 3 in the I direction and minus 6 in the j direction. Now it says that that is the velocity. Then the velocity is equal to the displacement divided by time. Fortunately, this divides in exactly into that. So this into that goes at 3. So the answer is 3 seconds. Incidentally, though, if we found that these weren't proportion, that, if dividing the x into the x here had given you a different answer to the y into the y there, then basically, then there wouldn't have been an answer. There wouldn't have been a solution for it. But anyway, in this case, the numbers work out, and it is 3 seconds. In some situations, you might find that this is this, or even this is a function of t. So we might have a little bit of equation solving to do. But anyway, in this example, it works out pretty straightforward as 3 seconds. Right, part B. The particle then moves from B to a point C with constant acceleration of 2j. So 2j, so it's just it's just accelerating in the upward direction. Doesn't mean to say the velocity is in the upward direction, but it's only accelerating. It's going to be constant velocity in the rightward or the I direction. Okay, so this is the acceleration vector. So that is why I've got the color coding there, from B to C. Now, if we it says it takes 4 seconds to move from B to C, this new point, find the position vector of C. Right, okay, position vector. So, so if we go to our equation, I've sort of tried to embolden these things because these are vectors here, and that using that convention that the vectors are written in bold letters. S equals ut plus half at squared. So we've got the initial velocity, we've got the time period, a half, that's a scalar. We've got the acceleration vector here, times time squared. And that's basically going to give us this. So this bit is that bit is that, and that gives us 4, 8. So the displacement from B to C is 4, 8, 4 along and 8 up. Okay, so so if we've got the displacement from B to C, we know the position vector of B, then we can find the position vector of C simply by adding those two together. So that's the position vector of B. This is the displacement in the second phase of travel. So this, therefore, is the position vector of C. Okay. And then it says find the distance from A to C. Well, of course, if this is C, it's the position vector of C, this is the position vector of A. So this is the displacement difference, if you like, between A and C, the displacement vector. So to get from A to C, we're overall, our journey goes 7 along and 2 up. Although it goes via B, but that's the overall journey that we do, and therefore the distance AC is the scalar, and it's we just apply Pythagoras basically. It's square root of 7 squared plus 2 squared equal to root 53. So that is quite a good example, and again, sort of fairly typical of the sort of thing that you will see. They do need a bit of practice. These, the reason being, it is easy to get a little bit confused, when you've got your 2 dimensions to work with. So yeah, it's the sort of thing that you need to have a bit of practice with. But anyway, hopefully that gives you a pretty good idea as to what kinematics in the vector plane is all about. If you wanted to see a nice meaty example where we're doing non-constant acceleration in the vector plane, then refer to the appropriate video to actually have a look at how that works. But that's it. So thank you for watching, and I will see you in the next video.